All right, legends, we are rocking and rolling. It's wonderful to have you here. Welcome to the statistical space, the magic venue where the rubber meets the road. I'm Mr. Mays, and I'm super excited to have you here. Hopefully you can hear me okay, and hopefully you can see okay. Today we're doing 1.2 notes, and 1.2 is going to cover displaying distributions. Specifically, of course, with graphs. It would be wise to have up your slideshow presentation for 1.2 alongside your notebook that you'll be taking notes in, on, or with. And I'm already on slide 7 because, as you might remember, slide 1 kind of has the title, and then 2 through 6 have those humorous statistics that were published outright, but were, of course, false for a variety of reasons that we went over in class. We're going to move over to 7, and then, of course, slide 8. Now, slide 8 perpetuates this idea of what is data? What is data? Data, of course, is numbers in context, and that is incredibly important. What I mean when I say that is that data is taking numbers, values, and doing more than just being here are a list of heights. It's well, what kind of heights? Heights of high school students at a large public high school, between the ages of 15 and 19, these kinds of details. All the details that we practiced looking at in these bad data sets that we were shown are the context we are looking for. And so when someone tells you a figure, you can tell them that isn't appropriate data yet because you haven't given me full context, and therefore you haven't fully proven that the data does anything. The more context, the clearer it is what the data accomplishes. And you can write down any of the things I've just said that you find useful to put in your notes. Don't just write down what I write on my sheet. Of course, we're going to talk about the different subcomponents of data. We need to understand that in a data set, there are individuals, there are variables, and then, of course, there's frequency or proportion. Now, the import of these things cannot be overstated, okay? Individuals are the thing you are studying. Right? If I'm looking at different heights of high school students, I am studying high school students, right? That's my individual. The individual, however, is not the heights. It is not the variable, which is, of course, the value I'm measuring, whatever is being measured, the component of the individual that's being measured. So with high school students and their heights, the height would be the variable. Cars and their color, the colors would be the variable, right? And the variable in that case would be color of car. Remember that variables have subcomponents, right? If a variable is height, you would have within that 5'9", 5'10", 5'11", 5'12", in other words, 6 feet. Those are the components of variable. They're not variables themselves. So remember that variables have values in them. So the value I'm measuring, oh my goodness, I wrote the value I am measured. What is that? The value I'm measuring, right? And it's made up of different components. And remember that variables can be either categorical or quantitative. Remember, of course, the categorical variables are variables that are not numerical, or if they are numerical, we can't do basic math with them. We can't add, subtract, multiply, and divide categorical variables in intelligent ways. Quantitative variables, on the other hand, are numbers that we can add, subtract, multiply, divide. Okay? And then frequency is always and we said this in class, of course, is always on our y-axis. And the frequency is not a variable. It is just telling us the amount of that variable that is present, or the amount of that part of the variable that is present. And with proportion, it tells you how the variable is broken down. 50% of cars are blue, 20% are green, things like that, right? And that would tell you proportions. Okay, so that's us getting through slide 9. In slide 10, I give you an opportunity to take a look at this. You should have said that the individual for the data set was drink or coffee, beverages, whatever. And then the variables would be type of beverage, which in this case is categorical because it's labeled as hot or cold. Calories, sugar, and caffeine, all of which are quantitative. Moving on to slide 11, I define categorical variables again for you and quantitative variables again for you. So let me know if those are still a struggle. But remember, there are some iffy parts there. Normally, categorical variables are very obvious. You're like, oh, what's the variable? Is it the color of the car? Obviously, that's categorical. Is it how happy you are? Right? When people always do like, are you smiling survey? It's like a smiley face, a regular looking face, a frowny face, a mid looking face, as the kids say. All of those, that's a categorical variable, is like happiness level, and then the different versions of it are the different smiley faces. On the other hand, though, be aware, there are some categorical variables that will astound you. And then, of course, quantitative variables are things like height, weight, number of deaths, number of lives birthed, right? Things of this nature. Numbers that we can add, subtract, multiply, and divide, and it means something. On slide 12, I give you the breakdown because on slide 13, you can see what is and is not quantitative versus categorical. Remember zip codes, those are categorical. So are like barcodes on an item, right? They label the thing, but they don't necessarily matter beyond just labeling the thing. They can't add and subtract zip codes. It doesn't do anything. Remember, of course, that a distribution tells us what values the variable takes. So the values of the variable. So this is what I was saying about like different car colors. The distribution will tell you, well, here where, my goodness, that is the ugliest variable I have ever written. Variable. Beautiful. So again, with car colors, you would say car color is the variable, but then you would say blue, green, red, orange, all the options. Those are on the distribution. The distribution shows the values of the particular variable, and then it shows the frequency, which is defined here as how often those values show up. The frequency, or of course, the proportion. Now you'll notice this first few sets of class notes are going to be very kind of like writing heavy. From here on out, it's going to be a little more, I mean, we're still going to have notes with lots of writing, but it's going to involve a little more math, a little more applied writing. Okay? And remember to always explore your graphs. Always explore graphs. Explore them. Break them down. And as you saw from the FRQ, which I will mention in these video notes, you need to not only break down those graphs, you need to identify all the components of the graphs and understand what you can do with them and what you can fail to do. What are you incapable of doing? What do you need to make assumptions to do? Moving on to slide 15, I break down the different kinds of categorical and quantitative variables. Be sure you took a look at the sheet from class that breaks down the different variable types. Specifically, it's the one where you were sorting and saying like, oh, this is the variable kind, this is the kind of graph I have here. I think it was called sorting different kinds of distributions. Let me know if you need help on any of those or if any of those don't make sense. The majority of them are only measuring one variable. Some are measuring two. And then they all look at these different kinds. But just be aware, categorical visualizations tend to include all kinds of bar graphs. Any kind of bar graph is categorical. And the occasional pie chart, although we don't see them very often, because they're not good for the most part. They're not informative enough. Versus quantitative visualizations, because you have to have different kinds if you're measuring numbers versus if you're measuring labels, right? For quantitative, we tend to have the box plot, the stem plot, the dot plot, and the histogram. Now, in class, I did not get a chance to spend as much time on the quantitative ones as I wanted to because we were a little rushed for day 2, but that's okay. I am going to go ahead and make sure that I get through it here in the video notes so you can go through it. You know the naming the graph activity, that's 16. 17, just be aware if you're interested, categorical variables have both ordinal and nominal variables, which is to say there are two kinds of categorical variable. A categorical variable is ordinal if it's like a medal or trophy, right? First, second, and third place. These are categorical because you can't add and subtract placement, really. It doesn't mean anything, or divide it. And they do have an order of like what's better or worse. So gold, silver, bronze would be ordinal categorical data. Nominal is just label, so everything else. So like car color. There's no, blue is not above red. You may like it better, but it's not like ranked above red. You can hear the bell for lunch ringing there. Okay, moving on to slide 18, association. This is a big deal. Association is how we analyze. You should write down what it says on the slide, of course, which is That association is knowing that when one variable is present, it impacts another variable. We tend to use the word association specifically with categorical data. Okay? When we use quantitative data, we call it correlation normally. Association is when one categorical variable is present, it impacts another. So a good example that I gave in class is just knowing whether or not students are in Mr. Mays' room impacts how loud Mr. Mays' room will be. So if we had two categorical variables, one being students in room, and the other being noise level. Let's imagine that for students in room, to make it categorical, we would just say yes or no, right? Yes or no. So we have two options, it's one or the other. For noise level, again, to make that categorical, I'm not going to use decibels. If I use decibels, that would be quantitative. Instead, for noise level, we would just say, noisy, average, quiet. I'll just do 3 for now, right? But we have those levels, right? Boom, boom, boom. And now because of that, I would then say, well, is there an impact? And I think we can all agree, right? If students are in my room, I am probably giving a lecture. And if I'm giving a lecture or we're doing problems, it's probably on the noisy side. We're going to have higher rates of noisy and lower rates of quiet in the room. Versus if students are not in my room, unless I'm giving video notes, which I'm doing right now, it's unlikely that it's very noisy. I'm actually very quiet when I'm not teaching you guys. So if that's the case, it might be on the quieter side. What that means is the distribution for the students being in the room and the noise level will be different looking than the one for students not being in the room and there being noise level. That difference proves or shows an association, not a causation. It doesn't show that one causes the other, although it may indeed do so. In this case, it does. But it doesn't prove that. All it shows is an association. And you might remember in class, I talked about how important association is. We need it. It brings the magic to the table. And you should stay curious in the world. So rather than being like, this is what's right, this is what's wrong, focus your energy on, I'm noticing when this happens, this other thing happens. Now, let's take a look at some associations. 19, 20, and 21 are great slides because they show you what an association looks like for a side-by-side bar graph on 19, a segmented bar graph on 20, and a mosaic plot on 21. You should be sure to ask me questions about any of these types of graphs if they are a concern for you, but be aware, let's look at the side-by-side bar graph for number 19. Because the distributions look different between the different age groups, 18 to 34, 35 to 54, and 55 plus, we know there's an association. In other words, to be specific, I saw that for 55 plus, USPS is the most likely delivery method, whereas for 18 to 34, UPS is the most likely delivery method. I also noticed that 18 to 34 had more people choosing other delivery methods than either of the other categories, even than either of the other categories combined. And what I want you noting there is I'm taking some liberties. I'm making some statements about, like, if you noticed, if you were to combine those other two, it would still be less than the bar for 18 to 34. Side note to make, I said this in class as well, but notice that age is turned into these ranges, okay? The way they've chosen to use the variable age, they're treating it categorically. It's not inherently categorical. In fact, inherently, if you said age, is it categorical or quantitative? I'd tell you it's quantitative. However, they've split it up into categories, and you'll notice with all bar graphs, there is a gap between the bars. That's imperative. You have to have a gap between the bars because you don't want people to think they are connected in any kind of way. The same thing is true with the segmented bar graph, although notice that all segmented bar graphs go to 100%. They tend to break down as proportions or as one whole. And the same thing with a mosaic plot. The one way that a mosaic plot differs, though, from its segmented bar graph compatriot is you'll notice the width of the mosaic plot. And what we notice is with mosaic plots with width for mosaic plots represents relative number of people. Of people surveyed. Ooh, I bet you have so much better handwriting than I do. Whoa! That was hideous. One more time for the cheat. No! Relative. a number of people surveyed. Cool. So relative number of people surveyed. What do I mean by that? Well, here's what I mean. If you look at this, and I'm on slide 21 right now, 18 to 34 has the second thinnest or the second thickest bars, right? Their bars are the second, like in second place in terms of thickness. That means they had the second most number of people interviewed or surveyed for this. The group that had the most people surveyed were 35 to 54. They were super wide. They were wider than the 18 to 34 group and the 55 plus group combined. And then of course the 55 plus group was like a sliver. And what those widths are telling us is more people were surveyed in the 35 to 54 category, fewer people in the 55 plus category. And then 18 to 34 was in the middle. The shaded area, so for example, if I look at USPS, for example, you would say, which group had the most USPS people surveyed? It would be the 35 to 54 group, because the shaded area of the box for 35 to 54 for USPS is greatest for 35 to 54 than it is for 18 to 34 or 55 plus, right? Even though 55 plus uses USPS more people were surveyed in the 35 to 54 group that had done USPS or used USPS. Cool. And as we agreed, all of the bars would look the same if indeed those bars were not associated. But they don't look the same or vaguely similar, so there is an association present between what group you're in and the preferred shipping method. This is one of the cool things about doing it in my classroom is the lights go off, so I get to look spooky for a moment. Give me a moment as you catch up. It's so annoying. You have to run to like the middle of the room. We're back, legends. Wait for it. Here it comes. We're on slide 22. I'm just going through all the concerns about those two different kinds of plots. Then, of course, we did the FRQ. Be sure you got the notes from someone who was in class on how I corrected the FRQ. You will notice, though, that 24, 25, and 26 and 27 give answers to that FRQ. 28 you should not need too much of, but just be aware that it gives some subparts of that if you need it. Okay, a little bit of extra information. 29 is where we really pick up steam, because this is where you guys kind of headed out from class, most of us, and we didn't get a chance to really flesh this out, so let's make sure we're clear on this. When we display quantitative variables, we are using histograms, stem plots, dot plots, and box plots. Be aware, quantitative variables can either be discrete or continuous. Ooh. Now, this is pretty easy to remember. I start with continuous. Continuous meaning it keeps going. And what I mean when I say continuous in this context is there are numbers between numbers. So 1.1 counts, 1.11 counts. All the values count. So for continuous quantitative variables, think of things like height. You can be in between heights. You can be 5'10", but you can also be 5'10 and a half, 5'10.6, right? Those values exist, okay? Now, you can choose to treat height as discrete, and if you did that, you would just say, it's the music, everybody's dreaded moment of having to hear the Titan song. This is hilarious too, because you're gonna hear this on YouTube if you can hear me, which means it may get me demonetized. I'm just kidding, there's no money. I don't make any money. I do it for you. I do it for the love of the students. And because I believe in you and your statistical acumen. If you were doing discrete variables, you would have 5'10", 5'11", 6 feet, and you would act as if there were no values between them. You would act as if you could not be between 5'10 and 5'11. That's how discrete variables work. Great examples of discrete variables is like number of people. If you're looking at number of people in a room, right? 10 people, 20 people, 30 people, things like that. That would be something that would be treated as a discrete variable because you can't have half a person and it's frowned upon in many states. Be sure, of course, that it's not a frequency that you're looking at and it is indeed just number of people. Other things that are discrete variables, again, I mean, it tends to be when you're measuring people, anything that you have to have whole amounts of. Let me put it that way as well. whole numbers or amounts. Like number of kidneys that you have, for example, right? If you have 1 kidney, 2 kidney, you can't really have half a kidney, okay? So that's the discrepancy between continuous and discrete variables. Continuous variables allow for movement between the numbers. Discrete variables do not. Okay. You'll see on 30, we have dot plots. They're pretty easy. I'm just going to say it out loud. With dot plots, put 1 dot for each data point for the frequency on each value. So as you can see there, I looked at hours spent on homework. Each dot represents 1 person who spent that many hours on homework. So if we look at 6 hours, there were 3 people who spent 6 hours on their homework per week. There were 5 people who spent 1 hour on homework per week. Pretty straightforward. Make sure, again, notice for 7 hours and 10 hours, don't skip any values. So you could get rid of 10 because there's nothing after it, but you can't skip 7. You have to show 7 and show no dots there. Okay? You must show all the values available, and that's for spacing reasons like we talked about. You don't want to miss any of the spots where data might exist. Next slide is stem plots. These are important. The key things to remember, okay? The leaf part represents each digit. You should only have 1 number per data point on the leaf part, which is the right, okay? And then the stem represents the first part of the number. You need a key. So in this case, for this key, we showed that 1 line 10 is equal to 10. Or 1 line 0, I should say, is equal to 10, which means the values on the stem side represent the tens place for this particular measurement, whatever it was. So 0,4 is 4, 0,6 is 6, versus 1 line 2 is 12, 1 line 4 is 14, and so on. 6 line 8 is 68. Similarly, you'll notice for 2, there's nothing after 2. So 2 line nothing means there were no values in the 20s for this stem plot, but we put it anyway because there were values before and after the 20s. Hopefully that makes sense. The things to be aware of here, no commas for stem plots. Big ticket items, no commas. Between digit values, we wouldn't need that because we know each digit is 1 data point. So you don't need commas, and you should never put commas. It's not professional, and you do get points off on the AP exam for putting commas. And then you must have a key. You must have a key. If you don't have a key, you lose points. And you need to check to make sure keys are present. And then, of course, no skipping values, right? So the 20s in this case. Don't skip it just because there are no values there. There are values before and after, so you need them. Okay, that's how we read a stem plot. Also notice for the shape of a stem plot, and we'll talk about this more in depth next class, but if you tilt your head to the side, look at the stem plot from the side, that's how you can read the distribution of the stem plot. Similar to like looking at a dot plot, it's really easy to look at a dot plot because it's up and down. A stem plot does what a dot plot does, but from the side, if you can see that visual, and with the numbers present. On slide 32, I endeavor you to make a stem plot yourself. Really quickly, here's what it will look like. You can pause the video here so that you don't get spoiled, and you can make one yourself if you want to try it out. Oh, there it went. It's gone. Let's try it again. We'll make it in green. That's cuter. You can obviously try again with me, but here's what it's going to look like. I'm going to put 15, 16, 17, 18, 19, 20, 21, and then, of course, 22. Be sure to make your line cuter than mine. Mine is hideous. I apologize profusely. And then on the digit side for the leaf, I would do 1, I would do 3, I would do 2, I would do 5, I would do 5, I would do 6. For 17, I would do 4. For 18, I would do nothing. For 19, I would do 6, I would do 9. For 20, I would do 1 and 4. And for 21, you'll notice there's nothing after 21. That means it's 21.0. I would put 0, and 22, I would put a 1 there. And that's my distribution. But I have to remember a key where I tell you that, for example, 15 line 1 is equal to 15.1. It does not matter what number you use for your key. You can use any value in the data set for your key. Okay, hopefully that all made sense. That's also real data I got from waiting in the line at Taco Bell because I love Taco Bell, and their wait times are fantastic in the Taco Bell near me. Okay, 33. We did not get to this in class, most of us. So let's make sure we're clear on this. This is what's known as a back-to-back stem plot. They are easier to read than you think, but they work downward. So if you look for female in this particular case, turn your head to the right, and that's your distribution shape. 64, 75, 78, 80, 89. But for the male side, the left side, it's a little weirder. It's actually backward because we're still going to move left to right. So for males, there are nothing for the 60s, and it's 72, 81, 90. So just to make sure that's clear visually, I'm going to just draw the male side really quickly, or part of it. We're going to have the two lines on either side. Male was on the left in your slideshow. Again, slide 33. 6, 7, 8, 9. I'm just going to write those in. It was 2, it was 1, it was 0. This represents 72, not 27. This represents 81, not 18, and this represents 90. Now that should make good sense logically because, of course, we need for our key to match the order of what we're doing. However, that middle line is always going to be your tens place then, and we'll move outward from there. Left for male, right for female. We'll talk more about how that affects things later on, but just be aware that that's how you read a stem plot when it's a back-to-back. Okay. On 34, a couple of cues for histograms. Histograms are amazing. We will use them so often. Histograms are like bar graphs. However, bars are touching. And I mentioned this to some people in class, but not all, so let's make sure this is clear. It's important that the bars are touching for a histogram. You must do that. And the reason you must do that is important. Each bar leads into the next bar in a histogram. It's quantitative data. You're going from like 20 to 30 to 40 to 50. That growth over a quantitative variable is important. So you want to touch the bars because they're related. On a bar graph, one bar is not related to the other bar directly. It's not like a progression, if that makes sense. They are also sorted into what are known as bins. So in histogram, each bar that we have has a series of quantitative values sitting within it, and we give the value of those bins. Okay? If you take a look on slide 35, this is a great example of how we can do this. Look at a bar graph on the left. We can see USA, India, UK, New Zealand, Japan. Those bars represent those countries, which are qualitative, also known as categorical variables, right? So we'll stick with the word categorical. It's better, and it's more statistical in nature. These bar graphs are categorically organized, so we leave the gaps. On the other hand, number ranges are what's present for histograms. So the bins for the histogram on the right are, one bin is 1 to 5. The next bin is 6 to 10. The next is 11 to 15. And what you would do is all the values that you got for your data that were from 1 to 5, you would place them in the frequency for your 1 to 5 bin bar. All the data points you got from 6 to 10 that were in your data set, you would put on the bar for your 6 to 10 bin, and so on and so forth. You will get more used to this as we go, and I will admit, these first notes and probably next time notes are kind of like drinking from a fire hose. It's a lot of stuff. A lot of it's intuitive, but it's stuff that you do need to remember and stick with, okay? If you have any questions at all, you need to go on Remind. You need to send me a message. Or you can email me if you cannot figure out your Remind stuff getting it ready. Please come find me. I am also free Monday, Wednesday, and Friday after school from 3:25 all the way till 4:30. Anything you need, I'm here for you. You let me know, okay? Guys, truly, bottom of my heart, I am so proud of you. I'm proud of you for taking this challenging course. If it's easy for you right now, rock on, take it, own it. I hope I'm entertaining you as well as I can, and I hope I'm giving you everything. I hope that's present in class. It ain't gonna stop. I'm here for you. I adore you. I'm thankful to be your teacher. And with all that in mind, be sure that you know 36 and 37. These two slides cover what we're going to mess with next class, which is CSOCs, which we reviewed on day 1, and looking at median versus mean. You are heroes. I appreciate you, legends. This is Mr. Mays signing off from the statistical space.